Good evening. So some of you are really late for your homework, like a Kelly, Demani, Jack, Nuzette, right? Tree is trying to catch up. Michael, Golem, yeah, you need to catch up with your homework. Number 5, okay, sure. Number 5, section 5.1. Yeah, let's do that. Point 1. Okay, find an explicit formula for an when a1 equals 1 and an equals the previous one plus n. Okay, let's go to the whiteboard. Let's try to figure out this together. 60. I think yeah, only Alejandro finished all 11 homeworks because we have 11 homeworks, right? So that should be 55, right? Should be 55. Oh no, plus 1 online. Plus 1 was online, so it should be 60. If you finish everything, every homework, that's a 60. Right, so that's supposed to be oh really? Zenep, you submit all 11? No, I didn't receive 11, I received 10. Oh, maybe 11, I just, yeah, it's homework 11 is not due yet, but I was asked, what is the highest grade? Right, it's not due yet, right? If you have finished 11, plus 1 online, so totally 12. 12 times 5, that's 60, all right? Right. Okay. All right, let's talk about number 5. Let's go to whiteboard. I might have some mistake. I might include it for someone or not included for someone else. Don't worry about it because all your homework is in my email. It's very easy for me to check, okay? If I mistakenly wrong you, it's very easy to verify. So given A1, A1 equals to 1, right? And AN equals to AN minus 1 plus N, or N greater than or equal to 2. So let's make some list. Let's make some list. Let me just make sure A1 is 1, right? Yes, it is. 5, A1 is 1. Yes, okay. That's right. A2. A2 is 1 plus 2, 3, right? A3 equals to the first one, the previous one, which is 3 plus 3, which is 6. Okay. So we could rewrite this. So that's find the first 6 terms of each of the following sequences. So this should be very easy, right? The first 6 terms. So A1, A2, A3, or let's say A4. A4 equals to A3 plus 4, which is, oh, wasn't sure how to find the explicit formula. Okay, let's try that. So we need to rewrite like a function in terms of n. So that's a 6 plus 4, which is 10. I see your question. Let's try to find a formula. So how do we rewrite this? So this one is A1 plus 2, which is A1, which is A1 is 1, 1 plus 2, which is 3. So we have 3, 6, 10. Well, let's do A5. A5 equals to A4, which is 10 plus 5, which is 15. Right? So meet all those. So we read the first couple of 5 terms. So we got 1, 3, 6, 10, 15. Now let's see. So the last one is n. So let's just rewrite this one. So A3 equals to A1 plus 2 plus 3 equals to 3 plus 3. Oops. Right? So if we rewrite A4, this is A3 plus 4, so 6 plus 4. Or we can keep it, so that's A2. I should rewrite one more term. A2 plus 3 equals to A1. So A2 is A1 plus 2. A1 plus 2 plus 3. Right? So A4 is it's A3 plus 4. So that comes from A3 comes from A2 plus 3, right? Then plus 4 equals to 6 plus 4 equals to 10. And also we can write one more term equal. So A2 is A1 plus 2 and plus 3 and plus 4. Okay, do you see a pattern? Who asked this question? Rajef. Do you see the pattern now? So you just read each term in terms of the every previous terms. You see the pattern? So A2 equals A1 plus n, which is 2. So 1 plus 2. If we only from 1, 3, 6, 10, 15, it's very difficult to figure out its pattern. But if we read out A3, it's A2 plus 3. So A2 is A1 plus 2 plus 3. You see the pattern, right? So A1 just 1. So I can even do one more step. I can do one more step. Because A1 is 1. 1 plus 2 plus 3. Right? That's 3 plus 3, that's 6. And you see, okay, A1 is 1, A2 is 1 plus 2, 3, A3 is 1 plus 2 plus 3, which is 6. And then A4, similarly, I can write one more step. So 1 plus 2 plus 3 plus 4. Okay. Now we can do for A5, but I don't want to do it. So let's so A1 equals 1. A2 equals 1 plus 2. A3 equals 1 plus 2 plus 3. A4 equals to 1 plus 2 plus 3 plus 4. A5, as you can imagine, should be 1 plus 2, should be, let me just add one step. Should be 1 plus 2 plus 3 plus 4 plus 5. All right, so the pattern is obvious, right? So how do we write an? A subscript n equals to 1 plus dot 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 up to n. We could use summation sign. We could use summation sign since we are learning summation. So summation n from 1. Oh no, not n from 1. We need a dummy variable. We need a dummy variable here. Let's see, we could do k or I. All right, let's say k. K equals 1 up to n. So k. Usually the index, we call this index. The index we use k or I. So k is a natural number. K equals to 1, 2, da da da. It's a natural number, right? So okay, does this help? The answer key give the formula as, okay, that's exactly what this is. That's exactly what this is. N times n plus 1 divided by 2. Okay. Yeah, I should write this instead of writing that. Okay, let's see why. All right, let's just add up a couple numbers. Actually, let's just go from this. Let's just go choose this one to do it. Let me change my color. Here I have 1, 2, 3, 4, 5. 5 numbers, right? I can pair them up. So I can pair 1 with 5. That give me 6. I can pair 2 and 4. That give me 6. Then so I have 2 of 6. Then plus the middle one, plus 3. So how many numbers I have? I have 5. So that's k goes from 1 up to 5, right? According to the formula. So this n plus 1, just adding, just pair them up. So 1 plus 5, 2 plus 4. N divided by 2, that's how many pairs we got, right? How many pairs? Because we're pairing each one, we pair them up. We'll pair the first one with the last one, right? So 2 divided by 2, that will be 1 pair. So we have, so how do we get 15? So we get 5 times 5 plus 1. Because totally I have 5 numbers, right? 1, 2, 3, 4, 5. And since I pair them up, how many pairs I have? I have 5 divided by 2 pairs. So now 5 plus 1 is 6. 5 times 6, 30. 30 divided by 2, 15. So the idea is because those are natural numbers, right? And the difference between each pair is just 1. So this actually is from Gauss. You know, one of the greatest mathematicians in history is called Gauss. When he was 5 years old, his teacher asked students, say, okay, let's add up 1 to 100, all the natural numbers, you know, add up from 1 up to 100. So what do? We just pair them up, right? Let me change the color. 1 with 100, that's n plus 1, right? Because 100 will be n. N plus the first one, that's n plus 1. So if I add, imagine this is 99. I pair 2 and 99, right? So that's n plus 1. So 99 plus 2. Because they're all same numbers. 100 plus 1 is 101. 99 plus 2, that's 101. 98 plus 3, that's 101. And how many pairs I have? I have 100 divided by 2. So when we add up 1 to 100, that's 50, 50, 50. Okay, so the actual number that's unpaired, in this case 3, is insignificant to the explicit formula. What do you mean? Paul, what do you mean? Oh, 3 is unpaired. Don't worry about that, right? Don't worry about that. Like whatever number the third term represents. Yeah. Yeah. Because those are natural numbers, right? The increment is 1. So we could do this. All right. Any questions? Let me take a photo so I could take attendance as attendance. Because last time someone left early. For those of you, you know, have homework problem, please do your homework. You know, I checked, I compared your homework with your exam grades. And those people who were able to, you know, to do every homework has much better grades than those ones who is behind finishing homework. All right. Let me see your comments. Oh, okay. Okay, anyone has any other questions from homework or from something? Again, please do your homework. Okay, homework is to practice. It's to make sure you understand the material we were talking about in the class. So we talk about a series, right? And we have a geometric series and we talk about two series. And then we have a formula to find so this is called a harmonic series, which converges. Oh, sorry. Thank you. Thank you. Only myself was looking at that. Okay, so this is important. all right, about geometric series. If the ratio, if the absolute value of the ratio is less than 1, it has a formula. It has a formula to calculate its limits, to calculate its value. All right. So today we'll talk about something called telescoping series, which is another important series. Right. So a telescoping series is a series in which most of the terms cancel in each of the partial sums, leaving only some of the first terms and some of the last terms. So basically, the series can be written as B1 minus B2 plus B2. You see the middle terms? Minus B2 plus B2, minus B3 plus B3. They get to cancel each other. So when we do the partial sums, we see we only get the first one and the last one in the partial sums. So in general, we have this. We have a sum of k terms equals the first term minus the k plus 1 term. So this is called telescoping series. The middle terms get cancelled. Let's see this example. So n goes from 1 up to infinity, of course, infinite series, right? We have cosine 1 over n minus cosine 1 over n plus 1. Or we can write a couple of terms and calculate a couple of sums. So the first term, cosine 1, second term, first term 1 over 1, right? That's cosine 1. Second term minus cosine 1 over 1 plus 1, which is a half. So S1 equals cosine 1 minus cosine half. What about S2? S2 equals cosine 1 minus cosine half plus cosine half minus cosine 1/3. So negative cosine half plus cosine half becomes 0. So we have cosine 1 minus cosine 1/3. S3, we have cosine 1 minus cosine half plus cosine half minus cosine 1/3 plus cosine 1/3 minus cosine 1/4. So negative cosine half plus cosine half cancelled. Negative cosine 1/3 plus cosine 1/3 cancelled. So left with cosine 1 minus cosine 1/4. So in general, we see sk equals cosine 1 minus cosine 1 over k plus 1. Right? You see cosine 3, that's cosine 1 minus cosine 1 over 3 plus 1. So sk has this term, cosine 1 minus cosine 1 over k plus 1. Since 1 over k plus 1, as k approaches infinity, 1 over k plus 1 approaches 0, and the cosine x is a continuous function. So cosine 1 over k plus 1, basically limit, but we take a limit of cosine 1 over k plus 1. And limit and cosine can be swapped. So we could do cosine limit of 1 over k plus 1. A limit of 1 over k plus 1 as k approaches infinity is 0. So cosine 0 equals 1. So therefore, we can conclude that sk equals to cosine 1 minus 1. So the telescoping series converges, and the sum is given by cosine 1 minus 1. So basically, we can take a limit. We take a limit of this series. The limit and the summation can be swapped. So we can take a limit of inside, then do summation. Any questions? So this is one of the examples. How come cosine 1 over n doesn't become 1? Okay, that's two different ideas. Okay, cosine 1 over n. So basically taking the limit. Yes, taking the limit. Maybe I should talk about this. Let's talk about this. Okay, cosine 1 over n. It's different, right? If we only talk about cosine 1 over n, what does it do? It just jumps up and down, right? It depends on the value of n. Right? You have all different, what do you call it? Called oscillating, going this way. Because cosine is between -1 to 1. It depends on the value of n. But we're talking about limit. We're talking about taking limit when n approaches to infinity. So the beautiful thing is, if the function is continuous in this, okay, when n goes to infinity, cosine 1 over n is a continuous function. That means we have no problem to swap cosine and limit. So we could do cosine, then we take a limit. Then we could take a limit. So we can swap this. Limit n approaches to infinity, 1 over n. All right? Because when n approaches infinity, cosine is continuous. So we have no problem to swap cosine and the limit. And what is the limit when n approaches infinity, 1 over n? That's 0. So that's why we have cosine 0. That's totally different from talking about only cosine 1 over n itself. Or maybe cosine 1 over x as a function. All right, it's totally different. If we talk about a function, there's totally two different cases. Does that help? I know, but the textbook says cosine 1 instead of cosine 0. Oh, really? Let's go back to the textbook. Textbooks sometimes have typos, all right? Have typos. No, it's cosine 0. Right here, cosine 0 equals 1. Can you see my cursor? The bottom. Oh, okay. We're looking at different places. Oh, that's a typo. Oh, no. Hold on. This is talking about different things. This here is talking about the cosine 1 over k. This cosine 1 is talking about this. That cosine 1 is from here. That's our first term, remember? That's our first term, cosine 1. Only this one is cosine 0 when we take a limit of it. When we take a limit of cosine 1, that's a constant, right? Limit of cosine 1 is still cosine 1. Oh, okay. Yeah. So two different things. Okay, great. Great. You're welcome. You're welcome. Great. Questions are great. All right. So anybody has any questions? I'm really hoping those of you grades below 75 try to understand the material in class. Try to ask me questions. Maybe I can explain better. Anyone has any questions? Let me just try to repeat. Okay, so we're talking about infinite series. So one important infinite series is a geometric series, which will have formula. If the ratio less than 1, if the absolute value of the ratio less than 1, we have a beautiful formula to calculate the number it converges to, which is the initial term, A1, divided by 1 minus the ratio. Okay, now we're talking about a telescoping series, which means the middle terms have negative, positive, which is additive inverse, right? A plus negative A equals 0. So all the middle terms are additive inverse, so they cancel each other. So in the end, when we do the partial sums, you know, we still get only 2 terms left, right? Telescoping. We add up 2 terms, we end up with, you know, the first one and the last one. We add up 3 terms, we'll end up with the first term, and the last term. So what do we have? We have A1, not even A1, part of A1 minus part of A3, right? So this is called a telescoping series. And a lot of them converges, because think about it, you have an infinite series, but because the middle terms are additive inverse to each other, you only have the first term survive and the last term survive. The first term is finite, the last term is finite. Finite minus finite has to be a finite, right? So this typical example is this, is cosine 1 over n minus cosine 1 over n plus 1. So we write out, you know, the first couple of partial sums. Then we see the pattern, right? That's sk equals cosine 1 minus cosine 1 over k plus 1. Right? Then we can take a limit of this. Then we take a limit, we say, okay, let a k approaches to infinity. So take a limit of this, let k approach to infinity. Well, cosine 1 is constant, still cosine 1. But negative cosine 1 over k plus 1, since the cosine is continuous function when n approaches infinity, we have no problem to swap the limit and the cosine. So we do cosine of the limit. We take a limit of 1 over k plus 1 when k approaches infinity. Then we get 0. So cosine 0, or cosine 0 is just 1. So that means this telescoping infinite series converges to cosine 1 minus 1. All right, let's keep going. Okay, everybody try this one, 5.11. So we have, so I have 20 of you in class now. I'm expecting 20 answers, all right? Maybe your answers are the same, or maybe your answers are different. Let's all try this. Let's all try to write out S1, S2, S3, okay? Then write down SK. Then we take a limit of SK, let K approach, oh, in this case is N. Let N run into infinity to see what we get. Yeah, sometimes, right? Because how do we deal with something goes to infinity? We always take a limit, right, James? We always take a limit of the thing. We use a dummy variable, right? Like integration, like improper integrations, right? If a lower limit, upper limit is infinity, what do we do? So that's one of the mathematical skill. We just take a limit, you know, make a dummy variable, see, okay, let the dummy variable approach to infinity. Then we substitute whatever we have in the integration, or in this case, in the sum, to be the dummy variable. Okay, let's all try this. But my plan is to finish this one, telescoping series, and go to 5.2. Okay, let me go get some water. Oh, I mean, what do I mean? Go to next section, I mean, 5.3. Go to 5.3. We need to start talking about some tests. E to the 1 minus 1. That's right. I agree with you, right? So if we do S1, just E, right? Just E. Yeah, E minus 1 is the same. E raised by 1 just E, right? E minus 1, exactly. Right. Do everybody agree with this? Does everyone agree with this? E minus E raised by 0. Right, E raised by 0 is 1. E minus 1. Damon, not sure about this one? James, all right, let's same agree, all right. Okay. What about Bixin, Alejandro, Alexander, Darren, Jack, Kelly, Nuzette, Paul, Shahaya. Anyway, let's go to whiteboard. So e to the 1 over n minus e to the so n goes from 1 up to infinity. And we have e to the 1 over n minus e to the 1 over n plus 1. Right, let's write down a couple of terms. So let's see S1. S1 is just the first term, right? Just A1. So equals e to the 1 over 1, just e to the 1. We don't have to write it. Minus e to the 1 over 1 plus 1, e to the half, right? Let's write S2. S2 is S1, e minus e to the half, right? This is the first term. You could think of this as a A1, right? So this itself is just an AN, right? You could think this way because we come from sequence. This is the nth term. So this is just A1. So this is A1 plus A2. What's A2? A2 is e raised by 1 over 2 minus e raised by 1 over 2 plus 1. 2 plus 1, which is 3. Right, that's S2. Well, what's going on with S2? We have a negative e to the half and positive e to the half. We have additive inverse. So those two cancel each other. So we have S2 equals e minus e to the 1/3. Right? I don't really have space to write S3. You should do it yourself. All right. So from here, we can figure out SK. Right? So SK looks like A1, another A1, E. The term survived in A1, so E, the first term, minus e raised by 1 over k plus 1. Right? You see, if this is 2, that's 3. You should read more terms, because I don't have a space. That's why I'm doing this. I'm skipping terms. Then I take a limit, right? I take a limit of this. I say, okay, let k run to infinity to see what happens. Right? I take a limit. Let k goes to infinity. Well, e is a constant number. It's still e. Then when we take a limit of this, right? When we take a limit of this, again, e is just a number, right? And 1 over k plus 1 is continuous in the interval from k, up to infinity. So I have no problem to think, okay, take a limit of the e term, just take a limit of the exponent. So take limit of this. What's the limit of this when k run into infinity? That's 0. So e minus e to the 0. What's e to the 0? Just 1. All right, anyone has any questions? Golem, we don't get e to the 0 minus e to the 0. Okay, the first term just e to the 1. E to the 0 would be e to the 0 would be 1. 1 minus 1 would be 0. Oh, I think that's a typo, right? We don't get e to the 0 minus e to the 0. We get e minus 1. We get e minus e to the 0's power. E to the 0's power is 1. So e minus 1. Okay, so the rest of you are so silent. I really like to help you to pass this course. But some of you, your midterm grades worries me. Please, if you have questions, please ask, all right? Otherwise, I have no idea how to help you. James, S2 is not e to the half minus e to the 1/3, right? You say S2? S2 equals A1 plus A2. You just add the two terms in the sequence. So S2 is, I should write here, is E, oh, okay, minus e to the 1/3. Okay. Okay, anybody else has any questions? If not, let's keep moving. So that's it. That's basically the telescoping series. All right. Now let's go to 5.3. Divergence and the integral test. All right. So we're going to use the divergence test. We're going to learn divergence test to determine whether series converges or diverges. Then use the integral test to determine if a series converges, the convergence of a series. Then estimate the value of series by finding bounds on its remainder term. Okay, let's see. Divergence test. For a series to converge, the nth term an must go to 0. Okay. Think about it. If each term, if the term in a series, doesn't approach 0 as the n goes to infinity, it would diverge, right? If you're adding, you keep adding numbers, you keep adding numbers, and the numbers goes bigger and bigger. There's no way you can converge to a number. But at a certain point, the term starting to go to 0. So we're just adding finite many terms. So that would be a number, finite number. So that's what it's saying here. When n approaches infinity, the term of an approaches 0, right? Then of course an plus 1 will be 0. The rest of the terms will go to 0. We are only adding up finite sum terms. So therefore, from the algebraic limit properties of sequence, we have this. We could think limit of ak when k approaches infinity. So ak is just a typical term in the sequence, right? Equals, of course, equals sum, k's partial sums minus the previous partial sums, right? So each ak can be written as k's partial sums subtract k minus 1's partial sums. That's just ak, right? It's just ak. And that's the limit of each one, right? So if each one approaches to s, because the rest of it goes to 0, then so this goes to 0. So that means, at a certain k value, the ak goes to 0. The term is starting to go to 0. So therefore, if a series converges, the nth term has to approach 0 as n approaches infinity. So the important consequence of this fact is that following statement. So it's a control positive, right? Control positive. So this is in if this, then this. So control positive is if not this, then not this, right? You can see my cursor move around, right? So if A, okay, great. So think about this statement. If this statement, then B statement. Okay, something called control positive. Control positive is if not this statement, think about this statement P. If P, then Q. Control positive means if not Q, then not P. Right? So you can make another statement. Okay, if a person is rich, he has money. If someone rich, he has money. If someone has no money, he's not rich. Like that. Okay. So we're going to do control positive of this statement. So if not of this, so if an does not approach to 0 as n approaches to infinity. So this means this sign means not approaches to 0. Similar to not equal, right? We have equal, then with slash equal sign, that means not equal. So this approaches to with slash approaches to, it means not approach to 0. So if nth term not approaches to 0 as n goes to infinity, then the infinite series diverges. Control positive statement. So this test is known as divergence test. All right. Does this make sense? Anyone has any questions? So we're going to learn a couple of tests, how to test, how to tell if a series converges or not converge or diverges. So we will learn a couple of tests. So this is the first one. The first one is called divergence test. So that's this. So we'll do control positive. Okay. Let's see an example. So what do? We want to show if we think that the series diverges, right? It doesn't. So all we have to do is to approve n's term not going to 0 when n goes to infinity. So if limit of an when n approaches infinity equals to some number, basically not equal to 0. Okay, or the limit does not even exist, then we can conclude the series diverges. Okay, pretty easy, right? So let's see an example. So here we have three series. The first one is n over 3n minus 1, right? If we take a limit of this, can someone tell the limit of this goes to where when n approaches infinity? 1/3. Remember that? Just take a limit of this nth term. Take a limit of n over 3n minus 1. How do we take a limit of that when n approaches infinity? We just take the leading term, right? Or we can think divided by n. N divided by n is 1. 3n divided by n is 3. The -1 divided by n is -1 over n. Or when n approaches infinity, -1 over n approaches 0. This is 1/3. Okay? When we take a limit of this, as n approaches infinity, that's 1/3. So it's not 0. Right? So it does not approach 0. So we conclude this series diverges. What about the second one? The second one will take a limit when n approaches infinity. Obviously, 1 over infinity raised by 3, that goes to 0. Okay, so B converges. And C, e to the 1 over n squared. Well, take a limit of this, we get an e raised by 1. E raised by 0, right? Well, e raised by 0 is not, it's 1. It's not 0, so this one diverges. So since n over 3n minus 1 approaches 1/3 not equal to 0, by divergence test, we conclude this series diverges. Since 1 over n cubed approaches 0, when n approaches infinity, oh, okay. So only by this, right, we cannot conclude. We cannot conclude. But in the future, we will talk about P series. From P series, we can see, okay, 1 over n cubed, the series, the B series, the series in B converges, all right, converges. But only by divergence test, because divergence test only tell the series diverges. So that's why this one is saying, B is saying, okay, 1 over n cubed approaches 0, so the divergence test is inconclusive. So we cannot see this series diverges, all right? But only by divergence test, we won't be able to tell this series converges. But because I know this series converges, so I slipped. My tongue slipped. But in the future, we will prove by something called P series. So this is one of the P series, and this one does converge. But only by divergence test. It's not enough to tell. It's just by divergence test, just see, okay, we don't know. We don't know. We cannot say it diverges. So, but so we say, okay, inconclusive. So divergence test only tell if a series diverges. So it's inconclusive. So C is the same thing, right? Because it approaches 1, not equal to 0. So it diverges. So same as 8, right? Same as 8. All right, everyone try 5.12. Divergence test. To show the term does not go to 0. If the term does not go to 0, we see the series diverges. Okay, if it does go to 0, we cannot see anything. Diverges. Take a limit when n goes to infinity. Right, take a limit of that. When n goes to infinity, we can swap the limit and the cosine. So limit of 1 over n squared is 0, and the cosine 0 is 1, which is not equal to 0. So it diverges. Yeah. Okay, anyone has a question about this? So limit of cosine, the an, limit of an does not go to 0. Damon, what do you mean no? No means diverges? Oh, you mean no questions? All right, no questions, we keep moving. All right, okay. Integral test. So in the previous section, we proved that the harmonic series, remember harmonic series? Is 1 over 1 plus 1 over 2 plus 1/3 plus 1/4 plus 1/5, so on and so forth. So the natural number is in the denominator. Harmonic series diverges by looking at the sequence of partial sums, Sk, and showing that as of the two partial sums of 2k greater than 1 plus k over 2 for all positive integers k. In this section, we use a different technique to prove the divergence of the harmonic series. This technique is important because it's used to prove divergence or convergence of many other series. All right, so this test is called integral test. Compares the infinite sum to the improper integral. Okay, remember improper integral? It's important to note that this test can only be applied when we are considering a series whose sums are all positive. Okay, so every term is positive. Okay, so this is our harmonic series, right? So, oh, this is only case term. So this is Sk, all right? This is Sk. Sk equals to 1 plus half plus 1/3 up to 1 over k. All right, 1 over k. And this one is greater than the integral from 1 to k plus 1, 1 over x. Remember the graph of 1 over x, right? When x is positive, when the k terms, k is positive, upper limit positive, all positive, on the first quadrant, go this way, right? Go this way. So therefore, for each k, the k's partial sum Sk satisfying this. Sk is adding up the first k terms, so 1 plus half up to 1 over k. And greater than this, so this integral we can anti-differentiate, right? We can integrate. So get ln x, then evaluate from 1 to k plus 1. So get ln k plus 1 minus ln 1. Well, what's ln 1? 0. So that's just ln of k plus 1. So the partial sum of k terms is greater than ln k plus 1. Since limit of ln k plus 1, when k approaches infinity, remember the graph of ln, right? Approaching infinity, and this sk is greater than this, is greater than infinity, right? So see this sequence sk is unbounded, right? Because it's greater than infinity. Therefore, the series of sk diverges. Yeah. And consequently, the series of harmonic series diverges. So this is just another way of proving harmonic series diverges. A lot of times we won't be able to prove directly. So what do? You know, think about something else. Let's say in this case, we think about integration of 1 over x from 1 up to k plus 1. We think about, okay, this partial sum is greater than this integral. Any questions? All right, let's keep moving. Okay. The picture is this, right? So when we draw the picture, we see, okay, 1 plus a half plus 1/3 plus 1/4 plus 1/5 is greater than the area under 1 over x. Now, let's consider this series, 1 over n squared. So before it's 1 over n, it's called a harmonic series, diverges. Now let's consider 1 over n squared. We show how an integral can be used to prove this series converges. And then later on, we're also going to call this P series. We sketch a sequence of rectangles as 1 over 2 square, 1 over 3 square, along with the function f of x equals 1 over x squared. Right? So that would be this. So the picture 1 over x squared, area under 1 over x squared, that much. And 1 square, 1 over 2 square, 1 over 3 square, this much. We see it's all smaller than 1 over x squared, right? If we can prove the integrals, the areas under 1 over x squared, not going to infinity, but goes to a finite number. So, and those guys are smaller than that. The summation of those areas smaller than that. Okay, so we see sk is 1 plus 1 over 2 square plus 1 over 3 square, so on and so forth, plus 1 over k square is less than 1 plus integration of 1 over x squared from 1 to k. Okay, let's see this picture again. So the first part is just 1 square. Right, the first part is 1 square. Then we start from 1. We start from 1. So we get a half. 1 over 2 square, 1 over 3 square, so on and so forth. So this sk is less than 1 plus this integration of 1 over x squared from 1 to k. Now we can calculate the integration part, the integral of from 1 to k of 1 over x squared, right? So that's just negative 1 over x, then we evaluate it from 1 up to k. So what do we get? We get a 1 minus 1 over k, minus 1 becomes plus 1. So we have 2 minus 1 over k, right? And which is less than 2. So sk is less than 2. That means partial sums are bounded. Partial sums are bounded. We also see that sk is an increasing sequence. So sk equals the previous sum, sk minus 1 plus 1 over k squared, right? From second terms above, k for k greater than or equal to 2. So since the set of sk's increasing and bounded by the monotone convergence theorem, it converges. This we learned a while ago, monotone convergence theorem. Cannot highlight. Once I highlight, it just pops. Here. So basically, so the theorem says increasing or decreasing and bounded, increasing and bounded series sequences converges. So here we use that. We say, okay, this set of SKs is increasing and bounded. So by the theorem, it converges. So therefore, this series converges. And later on, we're gonna see another proof called P series. We're gonna see this is also called a P series. Okay, any questions? So this basically is the proof. All right, let's keep moving. So basically, in general, right, if we can find the integral, right, if we can find a relationship between the partial sums with some integral, and we know the integral goes to infinity, so because this partial sum is greater than the integral, right, if the integral goes to infinity, and of course the partial sums will go to infinity. So we can prove that diverges. And similarly, if we can find an integral smaller than, like the second example, right? If we can find like the integral, we can find a finite number, we can anti-differentiate, right? We can anti-differentiate, we can evaluate, and we observe the partial sum is less than the one. So if a partial sum is less than the finite number, so we can use the integral test to prove that converges as well. So this is called the integral test. Okay, just try to remember those two examples. Okay, let's see this. Integral test theorem. Suppose the infinite series with all positive terms. Okay, this doesn't work with negative terms. All terms are positive. Suppose there exists a function f and a positive integer n such that the following three conditions are met. The first one is f is continuous and f is decreasing, and f is the same as the nth term for all integers n greater than or equal to n. So this big N means we can ignore finite terms. So up to a certain n, so a of big N. So maybe the first 100 terms doesn't work, but we can all truncate them. So this capital letter N functions like that. Means we can ignore finite many terms. Then the series and this both converge or both diverge. All right. So if we can find some integral, and the relationship is this. The relationship is a 1, 2, 3. You see the first two examples? Right? We have 1 over x and a 1 over x squared, right? Right, 1 over x. You see here, an is 1 over n. 1 over n equals to 1 over, just variable different, right? One is represented with x, another one is represented with n. But basically, an equals to f of n. For the second example, same thing. We have 1 over x squared, 1 over n squared. So f of x equals 1 over x squared, f of n equals 1 over n squared. Right? So that's this one. So the function is continuous and the function is decreasing. and we can ignore, you know, some terms, and if the function is the same as an, then if we can make a relation, we you know, two things have this kind of 1, 2, 3 relationship, then we can compare them. If one diverge, the other one diverge. If one converge, the other one converge. All right, so that's integral test. Okay, so this is one of the examples you can see. This is a geometric series, all right? Okay, let's see some examples. Using the integral test. So A is 1 over n cubed. Of course, what are we gonna do? We're gonna do compare with the integration, you know, 1 up to k, 1 over x cubed dx, right? So B is 1 over square root of 2n minus 1. So 1 over n cubed, we want to compare with integration 1 over x cubed. Then when we take, so the integration 1 to infinity of 1 over x cubed, improper integration, and we know how to do it, right? We take a limit, we use a dummy variable b, let it be run to infinity, then we substitute the infinity sign with b, then 1 over x cubed, and then we anti-differentiate, get negative 1 over 2x squared, and then we evaluate, we get negative 1 over 2b squared plus half, we take a limit of that, right? Limit of the first term will be 0, limit of the second term, still the second term because it's constant, so get a half. We get a half. So then the integral, because this one converges, so therefore we can conclude this one converges also. Where is the half come from? Okay, negative 1 over 2x squared, right? We evaluate at b, we get negative 1 over 2b squared. When we evaluate at 1, because minus become plus. We'll have plus 1 over 2 times 1 squared. What's 1 squared? 1 squared is 1. 2 times 1 is 2. So that's where half come from. Oh, okay. Yes, by this time everybody gets tired. Yeah, no worry. But it's good. It's good to ask. It's good to clear out the questions. So right. So because that one converges, so this one converges by integral test. Let's see the second one. The second one we can compare with this, right? Integration 1 to infinity, 1 over 2x minus 1. Or we can use u substitution. So we do the same thing, right? We anti-differentiate this. Excuse me. We anti-differentiate that, so we get a limit of this square root of 2x minus 1, evaluate from 1 to b. When we do that, we get a square root of 2b minus 1 minus 1. Now, problem. When b approaches infinity, square root of 2b minus 1 also approaches infinity. So this goes to infinity. Now we can conclude. Because this diverges, right? So this improper integration, this improper integral diverges. And or we see diverges, so the other one diverges, right? So this one diverges. Okay, anyone has questions? keep moving. Okay, why don't you try all this? Why don't you try 5.13? Then we talk about P series. Obviously, we want to compare with integral, improper integral 1 up to infinity, x over 3x squared plus 1, right? We let u be 3x squared plus 1. Then du would be 6x dx. But the numerator we only have x, so we just have to offset with 1 over 6, right? Anyway, you try it. Let me get some water. Let me also turn my light on. Okay, someone's done. Diverges? Oh, okay. Yeah, I see. You're right. You're right. Yeah. Because we would get ln 3x squared plus 1, then offset with 1 over 6, right? When we put in the value, right, we see it goes to infinity. So we can conclude that diverges as well. Great. Anyone has questions? Any questions? Okay, so I have two tests, right, in our toolbox. Now, P series. Another famous series. So we have, so far, what do we have? We have geometric sequence series. Ideally, in the geometric series, the ratio R, absolute value of the ratio R less than 1. Then it converges. And then we have telescoping series, right? The middle terms are additive inverse with each other. We're left with the first term, first one minus the last one. And now P series, right? So we have two tests. We have divergence test. We have integral test. Now P series. So the harmonic series 1 over n, and another series 1 over n squared, and also we see 1 over n cubed are all examples of P series. So for any real number P, so P can be any real number, P can be positive, P can be negative. The series So this one is called 1 over n raised by p. It's called a p series. So p series converges if p equals 2. We already see it before, right? And p equals, we haven't seen p equals 3 yet. But if p equals 1, it diverges. So what about other values of p? So in general, it's difficult. It's not impossible to compute the exact value of most p series. However, we can use the test presented thus far to prove whether a p series converges or diverges. So if p is less than 0, if p is a negative number, of course, 1 over n to the p, just n to the p, right? It goes to infinity. If p equals 0, that's just 1. Adding up all infinite ones, infinite many ones, it diverges. So therefore, by the divergence test, 1 over n raised by p diverges if p is less than or equal to 0. Okay. If p is not positive, the series diverges. So now comes to p positive. If p is positive, and if 1 over xp is a positive continuous decreasing function, therefore for p positive, we use the integral test to compare. Comparing 1 over n to the p to integration 1 over x to the p. We have already seen p equals 1, right? P equals 1 diverges, which is our harmonic series. So if p greater than 0 but not 1, right? P is positive but not 1, so let's try. So 1 over x to the p, improper integration, we take a limit, we use dummy variable b. So we get this 1 over 1 minus p. So get this one limit of this 1 over 1 minus p, then b raised by 1 minus p minus 1. Well, now think about, because b raised by 1 minus p goes to 0 if p is positive, right? If not positive, if p is greater than 1, right? Think about p equals to 2. If p is greater than 1, well, b raised by 1 minus, think about 1 minus 2, that would be negative 1. And if b goes to infinity, of course, 1 over b will approach to 0. But if p less than 1, right, 1 minus p, think about half. 1 minus half will be half. So b raised by half. Or if b goes to infinity, square root of b also goes to infinity. So we have this conclusion. So if p is greater than 1, the value is 1 over p minus 1. And if p is less than or equal to 1, it diverges. Okay, diverges. Let's go back a little bit. That's from here, right? So if p is positive, right? Not only positive, if p is greater than 1. If p is greater than 1. If p is greater than 1, right? We take a limit of this part. Limit of this part will be 0, right? Limit of this part will be 0 when b approaches infinity. So when b approaches infinity, limit of this part, b raised by 1 minus p, will go to 0. And 0 minus 1 will be minus 1, negative 1. And 1 over 1 minus p times negative 1, we can write as 1 over p minus 1. Okay, so beautiful formula again. So when 1 over x raised by p, when p is greater than 1, we have a beautiful p series formula. That equals to, that sequence converges to 1 over p minus 1. Right? Of course, if p is less than or equal to 1, it just goes to infinity. It diverges. So p series only converges when p is greater than 1. And it converges to 1 over p minus 1. A beautiful formula. Right? So for geometric sequence, you see somehow this is a little bit, you can relate this with the geometric sequence series, right? So geometric series, when the ratio is less than 1, when the ratio, absolute value of the ratio is less than 1, because the ratio can be negative, we have a beautiful formula to calculate the number it converges to. So for p series is the same. If p is greater than 1, we have a beautiful formula to calculate its limit, what it converges to. It converges to 1 over p minus 1. All right. So let's see these examples. So we have 1 over n raised by 4, right? So p equals to 4. Well, p is equals to 4 is greater than 1, so it converges. You know, what does it converge to? It converges to 1 over p minus 1. So 1 over 4 minus 1, which is 1/3. Right? But for b, the p is 2/3. P is 2/3, so less than 1. It diverges. Right? So diverges. So that's a p series. Geometric series, p series, very famous series. Harmonic series is a p series, but the harmonic series diverges. Anyone has any questions? Okay, let's keep moving. All right, so I won't, let me see if we have time to do this. So in general, if p greater than 1, it converges. And if p less than 1, it diverges. You're right. You're right. Less than or equal to. Okay, if p equals to 1, it also diverges. Okay. This one converges, right? Why? What's p? P is 5 over 4. It's greater than 1. It diverges. And then it converges. And then we can calculate the number it converges to. Converges to 1/4. Great, because it's 1 over 5 over 4 minus 1. 5 over 4 minus 1. Okay, think about that. 5 over 4. What is 1 over 1 over 4? 3 layers. That's 5 over 4 minus 1. That's 1 over 4. What's 1 over 1 over 4? Right, Jeff? 1 divided by 1/4. Yes, 4. So it converges to 4. Okay. All right, let's keep moving. Remainder estimate. Okay, that's it. That's it for 5.3. Anyone has any questions? So let's just think about what we have learned. So what's important? What's on the test? P series, of course. Okay, if P is greater than 1, it converges. If P is less than or equal to 1, it diverges. If P is greater than 1, the series converges to 1 over P minus 1. How beautiful is that? Right. Telescoping series, right? Geometric series. Integral test. We find a function, we find a continuous function to compare with. Then to take an improper basically so what are we comparing in the integral test? We're comparing finite world and the infinite world, right? And integral test, divergence test only able to tell us if a series diverges. All right, we only take a limit of the nth term if it's not equal to 0. It tells the series diverges. That's all. It won't be able to tell us if a series converges. Divergence test. That's it. Let me update this. So anyone has any questions? If no question, I'll let you rest early. How many more homework assignments do we have? Let me see. So today will be 12, right? What happens? I want to update. It's just gone. Let me just open again. Let me share my screen again. So we're homework 11, then tonight we have homework 12. So let me go back actually. Let me see if you are able to see this. Okay, I have to reshare my screen. Choose this one. Okay, now you should be able to see it. So 5.3, 12, comparison, 13, alternating, 14, ratio and root. Well, what did I count? 12, 13, 14, 15, right? 15. Power series, 16. I may combine those two. Maybe 17, 18, 19, 20, yeah, 20. I'm not sure polar coordinates and the area of polar. Oh, I think it's in. So maybe like a 22, about 22. So we'll skip the conic sections is not on our syllabus. So whatever on our syllabus, we just follow this. So I need to do a little bit of, fast, I think. I don't think we have much time. So let me share my screen with you for dates. Let me see if I can open this. If possible, I can share with you. Oh, I may not able to, but I can see myself. So let's see how many classes we have. Because it seems we have many to cover. We have 1, 2, 3, 4, 5, 6. So before spring break, we have 6 classes. After spring break, we have 1, 2, 3, 4, 5, 6, 12. Okay, so we're good. We're good. Yeah, we're good. 12, because I don't think we have 12 sections to go. Right, do we? Let me see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, we're good. Yeah, because for this class, we don't have to have so many exams. For the basic classes, like 4 exams, plus final 5 exams, they just, take out so much time, so much class time. So we have less exams and we have more class time. So we're good. Okay, anyone has any questions? Just keep doing your homework, all right? If you have been late for your homework, you still can do your homework, submit. You just won't be able to get full credits, get 5 credits, but you still get partial credits, all right? Okay, thank you. Okay, have a good night, everyone. Have a good weekend, everyone. Keep up with your homework. Only practice makes us, understand.